Hello dear students, welcome to the lecture video 9 of the chapter Magnetism and Matter. Today's topic to be discussed are Curie temperature, hard and soft ferromagnets, and hysteresis. Let us begin with Curie's temperature. Ferromagnetic property decreases with increase in temperature. We know this from the properties of ferromagnetic material, and at a very high enough temperature ferromagnet becomes paramagnet. So the temperature at which the ferromagnetic material becomes paramagnet is called Curie temperature, denoted with Tc. So the susceptibility above Curie's temperature, that is above Curie's temperature, the material will become paramagnetic. So the susceptibility in paramagnetic phase can be given by chi is equal to C divided by T minus Tc. So this formula is valid when capital T is greater than Tc. Yes, moving ahead, now let us study hard and soft ferromagnets. Hard ferromagnets. These ferromagnets are the one in which the magnetization persists on the removal of external magnetic field. Such materials we can call it hard ferromagnets. Example for that are iron, nickel, cobalt and copper. Next, soft ferromagnets. So the materials, when we apply them the external magnetic field, they get magnetized, and after the removal of external magnetic field on them, they once again get demagnetized. So the magnetization disappears after the removal of external magnetic field. Such materials can be called as soft ferromagnets. Example for these soft ferromagnets are soft iron. Moving ahead, now let us study hysteresis. The magnetic field B, that is we call it as magnetic induction in a sample, lags behind magnetic intensity, that is applied from the external source. Magnetic intensity H when ferromagnetic material is taken through a cycle of magnetization. This is called hysteresis. So this phenomena is hysteresis, and the loop formed by or loop formed during this process is called hysteresis loop. And hysteresis in Greek means lagging behind. So let us study now hysteresis loop. So let us understand what is it. So if we take a ferromagnetic material and subject it to one cycle of magnetization, that means we will magnetize it, demagnetize it and again demagnetize it. If we follow this procedure, then the following curve of BH forms a closed loop, which we denote with A, B, C, D, E, F. So that loop we call it to be hysteresis loop, which we can see here. So we are plotting a graph of B versus H, and we are plotting the phase of magnetization of the ferromagnetic material, and thus we get a loop. So that loop is called hysteresis loop. So let us study this hysteresis loop in detail now. So to begin with, let us consider a iron core solenoid carrying current I in it, and if we are having n number of turns and L is the length of solenoid, then we can write magnetizing force H is equal to small n into I, where small n is number of turns per unit length, which we can get as capital N divided by L into I. So this gives us the magnetizing force in the solenoid. So if this is the solenoid here, and this is the iron core which is in blue color, and this is the solenoid, and here we are having a galvanometer to verify the flow of current direction. So here H is dependent on the current value. So as we vary the current value, the magnetizing force will accordingly increase or decrease. Moving ahead, let us now take a BH graph with origin O. On the x-axis we have H, that is magnetizing force. On the y-axis we have magnetic induction of the ferromagnetic material, that is iron. So to start with, the solenoid is unmagnetized, that is it is having the domains which are randomly oriented. Okay, so now this O represents that state, unmagnetized state, which we can see here. So this is an unmagnetized state where the domains are randomly oriented, they are not aligned in a particular direction. So once we try to apply the magnetizing force by increasing the current, which we can see here, so we are increasing the current, and thus H will increase, by which B also has to increase in the material, because material will get magnetized. So by that we get to know that the value will increase and it will reach a point A where we are having the maximum B, that is maximum magnetic induction inside the material. That means the material has reached where the all domains are aligned in the direction of magnetization force, magnetic intensity. So the material has reached magnetized stage where the all domains have got aligned. Yes, moving ahead, now let us check what happens if we gradually decrease the value of current. If we decrease, then H also should decrease. If we do that, we find that the curve will follow AB instead of AO. So it doesn't go to the unmagnetized state, but it goes somewhere with a partially magnetized state. So we can see it here. So if we reduce the current to go on reducing and reach 0, that time we see that the material reaches point B rather than O. So at point B, H is equals to 0. Since current is 0, then there is no magnetic intensity. But we see that material has got some finite value of induction in it. So we call this as residual flux density. So this magnetic flux density left behind in the sample after removal of magnetizing force H is called as residual magnetism, or we generally call it as retentivity or remanence. So this point is the retentivity. So here magnetized state is the point A where all the domains had got aligned in the direction of magnetization force. When it reaches B, it reaches some stage where it is partially magnetized, where the domains have got partially disaligned or the moments have got partially disaligned. Moving next, here we see that domains have got partially disordered and their magnetic moment is because of the residual magnetism. So in order to reduce the flux density in the material to 0, I mean to say is, if we want to reduce B to 0, we have to now apply the current in reverse direction so that H also goes in reverse direction, and by reversing we are trying to do is what? Get the B value 0. So if we try that, we observe current has become very negative. We have got the value of current in negative, and we see now that the curve traces to a point C on the x-axis. So at point C, B is equal to 0, but our H value is minus HC, which is in the reverse direction. So here the point B is partially magnetized state. When we saw it, it was in this direction. Soon after this, it totally got unmagnetized. So this is a completely disordered state. After this, the value of magnetic intensity minus H at point C, where the magnetic field inside the sample becomes 0. We call this point as coercivity. So coercivity is this point. At this point we observe coercivity. Now if further H is increased by reverse direction, by increasing the current in reverse direction, we are trying to take a still more negative value of current so that we can increase the H value in the negative direction. So if we do that, the sample will get saturated in the reverse direction and it will attain minus V maximum. So if we are trying to do this, we get the point D, and that is the saturation point but in the reverse direction. So here the point C is unmagnetized point. From there, when we try to increase the current in negative direction, we get a magnetized state here, but this time the orientation or alignment of the domains is in the reverse direction to that of previous. Next, if we now try to reduce to 0, if we try to reduce H to 0 now, then we attain a point E and sample again retains to magnetic flux density D. That means if we try to make the magnetic field due to solenoid as 0, we still see that the iron core which we have kept inside the solenoid will have magnetic field or magnetic flux density in it. Because of that flux density, we see that the value will be OE, will be the value of flux density, even if there is H value equals to 0. But here we would have expected the curve to reach from D to O, but we see that it is not going to the unmagnetized state O, but rather it is trying to go to a point where it is having some remnants, some amount of residual magnetic field retains in it. So from here, magnetized state, that is from D, it has come to partially magnetized state, that is at point E. Moving next, we see that if we try to increase the current in the positive direction, then it goes from partially magnetized state E to the unmagnetized state F. Here B is 0, that is magnetic induction inside the material is 0 because it is completely disordered state. So from F to A, the process repeats as it has happened in the case of O to A. Therefore, the curve ABCDEFA is hysteresis loop, and the area enclosed by this hysteresis loop represents the loss in energy. The loss in the energy appears as the heat. Thank you students, and see you in the next video lecture.